The 2005 National Electrical Code, or NEC Handbook on page 199 contains an illustration error. Specifically, the illustration on the left side of the page incorrectly depicts the connections of the equipment grounding conductor, or EC, and the system grounding conductor, or SGC. It appears that these conductors have been flipped in the drawing. To understand this error, it's crucial to define what each of these conductors does and their proper roles within an electrical system. Let's begin with the equipment grounding conductor. The equipment grounding conductor is a vital safety component within an electrical system. Its primary purpose is to provide a low impedance path for fault current to return to the source. This path facilitates the quick operation of overcurrent protection devices such as circuit breakers or fuses. The EGC connects the non-current carrying metal parts of electrical equipment such as enclosures, conduit, and motor frames to the grounding electrode system. This connection ensures that if a fault occurs, like a live wire coming into contact with the metal enclosure, the fault current will flow through the EGC back to the source, causing the overcurrent protection device to trip and de-energize the circuit. Without a properly functioning EGC, a fault could cause the metal enclosure to become energized, posing a significant shock hazard to anyone who comes into contact with it. Now let's turn our attention to the system grounding conductor. The system grounding conductor, also known as the neutral grounding conductor, connects the neutral point of a separately derived system such as a transformer or generator to the grounding electrode system. The SGC is responsible for grounding the system's neutral point, establishing a stable voltage reference. Grounding the neutral helps to limit voltage fluctuations and prevent overvoltages that can damage equipment. In a typical electrical system, the SGC is connected to the neutral bus at the service entrance, and from there, it connects to the grounding electrode system. The grounding electrode system typically consists of grounding rods, ground rings, or metal underground water pipes that are buried in the earth. The purpose of the grounding electrode system is to provide a connection to earth, which helps to stabilize the voltage and provide a path for fault current to flow back to the source. In the erroneous illustration on the left side of page 199, the equipment grounding conductor is incorrectly shown connected to the neutral point of the system. This is incorrect because the EGC primary purpose is to connect the non-current carrying metal parts of equipment, not to the neutral point. Furthermore, the system grounding conductor is incorrectly shown connected to the non-current carrying metal parts of equipment. Again, this is incorrect. The SGC should only be connected to the neutral point of the system. The illustration on the right side of page 199 of the 2005 NEC Handbook shows the correct way to connect the equipment grounding conductor and the system grounding conductor. The EGC is shown connected to the non-current carrying metal parts of equipment, and the SGC is shown connected to the neutral point of the system. This is the proper configuration. It's important to understand why this distinction is so critical. Firstly, the equipment grounding conductor ensures that any fault current on the metal parts of equipment flows directly back to the source, causing the circuit breaker to trip quickly. Secondly, the system grounding conductor ensures that the neutral point of the system is properly grounded, providing a stable voltage reference. By connecting these conductors correctly, you minimize the risk of electrical shock and equipment damage. Here's a breakdown of how this might look in a typical scenario. Firstly, at the service entrance, the neutral conductor from the utility transformer is connected to the neutral busbar in the service panel. Secondly, the system grounding conductor connects the neutral busbar to the grounding electrode system, establishing the ground reference. Thirdly, separate equipment grounding conductors run with each circuit, connecting the grounding terminals of outlets, switches, and light fixtures back to the grounding busbar in the service panel. Fourthly, the grounding busbar is then connected to the grounding electrode system, providing a common ground point for all equipment. The National Electrical Code provides specific requirements for the size and installation of both equipment grounding conductors and system grounding conductors. For example, NEC Table 250.122 specifies the minimum size of equipment grounding conductors based on the rating of the overcurrent protection device. Similarly, NEC Section 250.28 provides requirements for the size of the system bonding jumper, which is the conductor that connects the neutral busbar to the equipment grounding busbar in the service panel. It is essential to adhere to these requirements to ensure the effectiveness of the grounding system. The grounding electrode system itself must also meet certain requirements. NEC section 250.52 specifies the types of grounding electrodes that are permitted, such as ground rods, ground rings, and metal underground water pipes. The grounding electrode system must have a resistance to earth of 25 ohms or less, as specified in NEC section 250.53. If the resistance is higher than 25 ohms, an additional grounding electrode must be installed. To summarize, the equipment grounding conductor and the system grounding conductor play different but equally important roles in an electrical system. The EGC protects against electrical shock by providing a low impedance path for fault current, while the SGC ensures a stable voltage reference by grounding the neutral point of the system. It is essential to connect these conductors correctly to ensure the safety and reliability of the electrical system. The error in the 2005 NEC Handbook highlights the importance of carefully reviewing and understanding electrical diagrams and illustrations. While handbooks are valuable resources, they are not always error-free, so it's crucial to verify information and consult with qualified professionals when necessary. In addition to the specific error on page 199, it's a good practice to regularly review and update your knowledge of the National Electrical Code. The NEC is updated every 3 years, and each edition contains revisions and additions that reflect the latest advancements in electrical technology and safety practices. Familiarizing yourself with the latest edition of the NEC is essential for ensuring that your electrical work complies with current standards. Moreover, it's important to note that the NEC is not a design manual. It provides minimum safety requirements for electrical installations, but it doesn't provide detailed design guidance. Electrical system design requires a thorough understanding of electrical engineering principles and practices. Consulting with a qualified electrical engineer is recommended for complex or critical electrical installations. Finally, always remember to prioritize safety when working with electricity. To energize circuits before working on them, use appropriate personal protective equipment, and follow all applicable safety procedures. Electricity can be dangerous, but with proper knowledge, training, and precautions, you can work safely and effectively. Let's delve a bit deeper into specific examples and scenarios to further illustrate the roles of the equipment grounding conductor and the system grounding conductor. Consider a common household appliance such as a washing machine. The metal chassis of the washing machine is connected to the grounding pin of the power cord. This grounding pin is connected to the equipment grounding conductor in the branch circuit. If a fault occurs inside the washing machine, such as a live wire coming into contact with the metal chassis, the fault current will flow through the EGC back to the service panel, tripping the circuit breaker and de-energizing the washing machine. This prevents the chassis from becoming energized and posing a shock hazard to the user. Now let's consider a separately derived system, such as a generator. When a generator is used to supply power to a building, it becomes a separately derived system. The neutral point of the generator's winding must be grounded to establish a stable voltage reference. This is accomplished by connecting the system grounding conductor from the neutral point of the generator to the grounding electrode system. This grounding connection ensures that the voltage between the neutral and ground remains close to 0 volts, preventing voltage fluctuations and overvoltages. In industrial settings, you often find large motors connected to electrical systems. These motors have metal frames that must be grounded to protect against electrical shock. The equipment grounding conductor is connected to the motor frame, providing a path for fault current to flow back to the source. The size of the EGC must be adequate to handle the potential fault current. NEC Table 430.250 provides guidance on the minimum size of conductors for motor circuits. In addition to providing a path for fault current, the equipment grounding conductor also helps to reduce electromagnetic interference, or EMI. EMI can disrupt the operation of sensitive electronic equipment. By providing a low impedance path to ground, the EGC helps to minimize the effects of EMI. The National Electrical Code also addresses the use of isolated ground receptacles. These receptacles are designed to minimize noise and interference in sensitive electronic equipment circuits. Isolated ground receptacles have a separate grounding conductor that is isolated from the normal equipment grounding conductor. This isolated ground conductor runs directly back to the service panel, minimizing the potential for noise and interference. When installing electrical systems, it is essential to ensure that all grounding connections are properly made and that all grounding conductors are properly sized. Loose or corroded grounding connections can compromise the effectiveness of the grounding system. It is also important to protect grounding conductors from physical damage. Damaged grounding conductors can reduce the effectiveness of the grounding system and pose a safety hazard. Regularly inspecting and testing the grounding system is recommended to ensure that it is functioning properly. Grounding system testing typically involves measuring the resistance to earth of the grounding electrode system. If the resistance is too high, corrective action must be taken to improve the grounding system. In conclusion, understanding the roles of the equipment grounding conductor and the system grounding conductor is essential for ensuring the safety and reliability of electrical systems. By connecting these conductors correctly and adhering to the requirements of the National Electrical Code, you can minimize the risk of electrical shock, equipment damage, and other electrical hazards. The 2005 NEC Handbook illustration error serves as a reminder to always verify information and consult with qualified professionals when necessary. The equipment grounding conductor provides a low impedance path for fault current back to the source, tripping the overcurrent protection device. The system grounding conductor connects the neutral point of system to the grounding electrode system, establishing a stable voltage reference. Proper grounding is critical for safety and equipment protection. Always consult the latest edition of the National Electrical Code and seek guidance from qualified professionals to ensure safe and compliant electrical installations.